Our next speaker is Soup's Ranjan. He's been in advertising for 5 years and currently works at Yelp. The title of the talk is Data Science in Advertising, or A Future When We Love Ads. I read that with a straight face, and the rest is up to you.
Good afternoon, everyone. So I'm here to talk about advertising and how we apply data science to advertising so that at the end of the day, we can delight users with ads. So I work for Yelp in our ad team. And Yelp has a local advertising product where we show our ads when people search for certain things. We show our ads across all the different platforms. As for example, we show it on our desktop site, on our mobile apps, on our mobile site, etc. Our ads, they appear on top of our search results. So you can see a few ads over here. And our advertisers are local, small, medium, national, local advertisers. Yelp has a very unique advertising product, and people who come to Yelp, they have a strong intent to purchase. So about 89% of users who research a business on Yelp, within a week, they're very likely to purchase something at that business. So our advertisers are the whole gamut of small mom and pop shops, restaurants, professional services like movers, gardeners, plumbers, etc. And these advertisers, they can purchase our ad package either in bulk on an impression basis. Whenever I talk or would mention impression, I really mean page views. And they can also purchase ads on a cost per click basis, where they would only pay whenever somebody sees an ad and clicks on it, right? And then they could also purchase ads on a leads basis, and we have a leads product where we charge our advertiser every time somebody makes a phone call to the business, right? So we have ads in different denominations and different packages. So when you purchase ads in a bulk impression fashion, then you pay us a monthly fee, let's say $350, and you get 1,000 impressions. We also have a cost per click model, which I mentioned earlier, where once again you pay $350 and we give you as many clicks as possible, right? So now local advertising has a lot of unique challenges compared to social, search, and mobile app advertising. And in the next few slides, I'll try to motivate you why local advertising is unique. One of the most important aspects and interesting aspects of local advertising is location, right? So users' interest in a business, it reduces with distance. When I'm searching for a restaurant, I'm not very likely to go to a restaurant which is more than, let's say, 50 or 60 miles away, right? But when I'm searching for a plumber, since I'm not the person who's going to be doing the driving, I'm perfectly okay with the plumber driving from, let's say, 70, 80 miles further away from me, right? So this is what I'm showing over here in this graph, where I have on the x-axis the distance between the user and the advertiser. And on the y-axis, I have click-through rate, which is a signal or a measure of interest of the user. Click-through rate defined as number of clicks divided by number of impressions, where I have basically computed click-through rate for every bin of distance. So, right? So when the distance between the user and the business was 10 miles, then I have computed click-through rate, and so on, right? So as you can see, the green line, which is that for home services, which includes plumbers, movers, gardeners, etc., it's above the blue line, and the blue line, it drops down to 0 pretty quickly, right? So now there are other effects in advertising in the local space which are seasonal. So people are interested in manicure and pedicure during the summer, and they are more interested in heating and HVAC contractors at the onset of winter, right? So here I'm using Yelp Trends, which is actually a very cool thing to play with. When you get a chance, go out and go ahead and go to yelp.com/trends. You can enter any query, enter the name of a city, and then you can see how are people searching for it over time. And you can see the peaks for searches for pedicure in San Francisco are around summer, right? And then here, I'm showing you another interesting aspect where local search has another component, which is that of calendar effects, game day schedules, etc. So here I'm showing you, for example, searches for SF Giants. They peaked, around the time when we won the World Series. And interestingly enough, those searches are also correlated with searches for sports bars, right? So in essence, if we could predict that there's going to be a game day, then we could predict that people are very likely going to be interested in bars, and therefore we could predict demand for sports bars and demand for searches for sports bars, and we could use that in a variety of ways in order to sell advertising to those local bars, right? Now, traffic also varies by categories. As you can see, people are more interested and searching for restaurants on the weekends. They are also searching for nightlife categories on the weekends, less so on Sunday, but more so on Friday and Saturday. And their interest in health is much less over the weekend, right? Once again, why is this important? This is important because if we can predict demand, then we can do a better job at serving ads, as you will see through the rest of the talk. Then another interesting aspect to local advertising are categories. So in some cases, some categories are very intuitive. When you search for sushi, we will return to you results for Japanese restaurants. That's clear. That's intuitive. But sometimes when you search for sushi, then our advertising product may return to you a response for a karaoke bar as well, right? Which is not so intuitive at the onset. However, it turns out that people who search for sushi are also interested in karaoke bars, right? Over here, I'm showing you queries wherever we have shown karaoke ads, right? So on the y-axis, I have a measure of similarity between karaoke bar and all these other search query terms, right? And on the x-axis, I have the click-through rate. So of course, things like nightlife, dive bars, dance clubs, they have a very high correlation with karaoke, right? People who are interested in karaoke are very likely interested in those categories too. And they are not so interested in sushi and Japanese in terms of category similarity. There are very few businesses which are labeled as both sushi as well as karaoke. However, regardless, the click-through rate of showing a sushi or a Japanese ad on a karaoke, the click-through rate of showing a karaoke ad on a sushi search is also pretty high. It's predominantly, higher than the similarity between the two. So, what I'm trying to motivate here is that when we are serving ads, we're doing a lot of different things. We're measuring relevance, we're measuring interest of the user, but we're also taking into account what are the sort of other things which are similar and not so similar, but still may lead to a higher click-through rate, right? Another interesting aspect is budgets. So if you do a query for Chinese restaurants, maybe the budget for all Chinese advertisers in that area near you is over, right? They've all finished up their budget. It's, let's say, towards the end of the month or what have you. Then in that case, we may still show you an ad, but we'll show you an ad for a closely related category for a Vietnamese restaurant, right? So we call this category expansion. Now, we have to expand across categories which are relevant, but at the same time, they should fulfill the demand of the advertisers, because we also have to make sure that all the demand of Vietnamese advertisers, all the budget that they had, we should also fulfill that, right? So therefore, there are three stakeholders, as I've been referring to all throughout. There are the users for whom relevance matters. Then there are advertisers for whom things like budget, how many clicks they get, how many phone calls they get from those clicks, etc. They matter. And then for Yelp, the revenue matters, right? So inside our ads team at Yelp, Corgi is our mascot. So we like to call it that we want to have a well-proportioned Corgi. We want to balance the 3 points of the Corgi, right? So now advertising is a matching problem, right? So we have users on one side and we have ads on the other side. The constraints are that the users, I would also refer to users as opportunities. So opportunities is finite, and then budget for advertisers is finite. And the other constraint is that we don't know future traffic. We don't know what to expect in future in terms of what are people going to search in future, right? And then the goals are that we want to maximize revenue for Yelp. We want to show a user the most relevant ad possible. But at the same time, we want to also fulfill the budget for the advertisers, right? So it turns out that the greedy strategy works out pretty well. So we do a second price auction in which we select the ad which maximizes the revenue, as I will show you in the next few slides. So the life cycle of our ad system is the following. When you enter a query for, let's say, bars, then the first thing that happens is we go through the list of possible advertisers. Let's say the advertisers possible are Blue Light and City Brewery, and the budgets are $100 and $200 each. We would narrow down to only have or keep advertisers who still have budget, right, who haven't finished it. We'll also narrow down by only keeping advertisers who are within a few miles of you, because we don't want to show you an ad for like a restaurant which is like hundreds of miles away. And we'll also show you, or we'll also narrow down the list of advertisers by showing you or returning ads, possible ads, which are within the same category as you wanted to search for, right? And then the second piece here is the auto bidding system, where we also help our advertisers pick the bid price. The third piece is the click-through rate prediction, where for each of these ads, we figure out what is the expected probability that somebody will click on that ad if I were to return it, right? Now, both the bid price and the click-through rate, they go into our auction system, which is a second price auction. And then we pick the winner of the auction. So let's say the Blue Light wins the auction. Then Blue Light will be shown, will be returned as the result. However, Blue Light will not pay what he bid. Blue Light will pay what the runner-up would have paid. So a second price auction, it is shown that second price auction, the most optimal strategy for every advertiser is to bid your true value, right? So therefore, I just want to go into a little more details over here. So let's say Blue Light was bidding 100 cents and City Brewery was bidding 200 cents for this one particular query, right? And our other system, the click-through rate prediction system, it says that the expected click-through rate, if I were to return Blue Light as an ad, is 0.1, and the expected click-through rate, if I were to return City Brewery as an ad, is 0.04. Then I would compute the expected revenue, which is nothing but the product of these two things, right? So therefore, it's 10 cents for Blue Light, and for City Brewery, it's 8 cents. So Blue Light will win. However, it would not pay it would not pay what it bid. It would pay, pretending as if the runner-up is we take the revenue from the runner-up, and then that is 8 cents, and then we divide by this click-through rate for Blue Light, which is 0.1. So Blue Light would actually pay 80 cents. And it can be shown that, the second price auction system is optimal in terms of everybody will bid the true value, etc. Now, I will walk you through each of these various components in more details. So the first one, as I referred to, is our ad selection process, where we figure out the set of advertisers which are interesting and relevant to the user and have budget. So we index all our advertisers in Elasticsearch, and they're indexed by the geoquad, which is basically a representation of the latitude and longitude of the advertiser, right? And based on the user's location and the advertiser's location, we would figure out the distance using an Elasticsearch query, and we would also figure out the categories of the user and the advertiser. And then we would finally whittle it down to a representative set of ads, which are the only ones which will not participate in the auction, right? So suppose you did a query for a business here in Montreal, then an advertiser in Kansas City is not going to compete in that auction. So now the second piece here is the auto bidder. So the reason we came up with an auto bidding system is that our advertisers are local businesses who want to delight the customers. A sushi chef wants to make the best sushi, sashimi, and the nori, not necessarily to optimize click-through rates or cost per click or any of those other terms, which they may not even be aware of. So the solution is we just ask them very simply, you just tell us how much you want to spend per month, and we'll give you the most number of clicks that we can, right? And the way we do it is as follows. So this is the budget curve. So I have on the x-axis the bid price. And then on the y-axis I have clicks, right? So if in the auction the advertiser were to bid very high, then he will actually get less number of clicks because his budget is finite, right? The more you pay for each click, the less the number of clicks you will get, right? Now this red curve is the competition curve, where the more you bid, actually you're going to win more auctions, and therefore in some sense you will also actually get more clicks. So of course you can see these are two contrasting curves, and therefore the sweet spot is somewhere here, right? such that you can fulfill your budget as well as you can win as many clicks as you can. So therefore, you should set your bid such that you come to this sweet spot, right? So another way to think about our auto bidding system is that it is helping us, only find the clicks for a particular advertiser which are cheap and not very expensive. So therefore, at this point in time, if the advertiser can forego these expensive clicks because he knows that there are some cheap clicks which are going to occur in future, right? Now, how do you find this intersection? So of course, this blue line is easy to draw. It is nothing but the budget curve. So the budget is finite, let's say $350 a month. Then you set a different bid price, and then you get how many clicks you will get for that bid price, right? The red one, we get using our historical auction data. So based on the past auctions and who won the auction, we can get that, right? And then, we do this computation for the red line for each advertiser independently. And we do, and of course, each of these auctions are not truly independent of each other. So in order to work around that, we then repeat this whole process as frequently as we can, right? Cool, so now the next piece is our CTR, or click-through rate prediction system. So this system uses machine learning, and we've basically formulated it as a binary classifier problem. So given all our past ad impressions that we have shown, we know which of those ads they resulted in a click or no click, right? So we have a binary variable that we are trying to predict, which is click or no click. So the training data, it consists of features for the user, features for the advertiser, features about the query, etc., right? And the training data is basically, all past ad impressions which have been sampled over past several months, and we have a separate holdout data set on which we evaluate our training model, right? The holdout data set, it is minimally overlapping with the training data set so that, you don't introduce biases, right? So now the performance metric that we measure is mean cross entropy. So this formula here, y is our prediction variable. It can take values of 0 and 1, which is click or no click. And p is our predicted click-through rate, right? So this formula would be optimized or minimized because lower values are better. It will be optimized if I could, for every ad which leads to a click, if I could say with a certainty of 1.0 that it is going to lead to a click, right? Then this thing, y log p, will lead to 0, right? And likewise, this term 1 minus y log 1 minus p, for everything which doesn't lead to a click, if I could say with certainty that the probability of getting a click for this guy is 0, right? Then 1 minus p is 1 here, and log of 1 is 0. So then that term will again go to 0, right? So our complete system is the following. So we take our past ad impressions data, which is stored in S3, and we have a map-reduce job, which is written using our open-sourced package called Mr. Job. And we take a sample of our ad impressions, we extract features, and then we build a model using, we've experimented with scikit-learn as well as Vopal Wabbit, and we're also experimenting with Spark, as I will talk about later. And then once we extract the features and train a model, then the model is basically converted into a human-readable format so that we can analyze it. And then the model format is also copied over to our ad service, which at runtime, or which I would also refer to as online scoring piece, at that time, for all the candidates in the ad store for a given user query, all those ads will be scored using this model file, right? And then I will basically get the click-through rate for all the candidates in the auction, right? Now, feature framework looks as follows. So given a query and an ad, I would extract features about the user, about the advertiser, etc. And then I would apply several transforms, right? The transforms could be in terms of standardization. So suppose a feature is the distance between the user and the advertiser, then a standardization would make all the distance values be in the space of 0 to 1. Another transform could be polynomials. So you'd raise distance to the power of 2 to the power of 3, etc. And the reason you may want to do that is because maybe with a distance to the power of 2, the relationship between this feature and click-through rate becomes more linear, right? That's how we try to capture non-linearity. Because one thing I forgot to mention earlier, we're using logistic regression. And logistic regression assumes that all the features are independent of each other, and in order to incorporate nonlinearity, you have to do these transforms, right? And we also, when we're doing the feature extraction, we also make use of our historical click-through rates for campaigns in the past, for different categories in the past, etc. Now, an example of a feature. So one of the features is, for example, whether the campaign that we're running is from a brand name campaign or is it from a local business, small local business. So, so we have basically, so this is how it looks like. So we have every feature is a class, and then if it's a brand name campaign, then it gets a value of 1, otherwise it gets a value of 0. I have chosen a very simple example over here, but at the end we return a list over here, which then finally gets converted into a sparse array. So our model training, so we have used scikit-learn in the past, and now we are experimenting with Wapl-Wabbit and Apache Spark. So in the framework where we were using scikit-learn, we would extract all the features as a sparse SciPy matrix, and then we were using stochastic gradient descent classifier from scikit-learn, and we were using this on a multi-core system, such that each core would basically try to run SGD on a particular grid point. And by grid points, I really mean, there are several hyperparameters in SGD, which are, which could be around regularization, etc. Right? So for each such grid point, we run it on one core. We run the training on one core. Now, the other framework that we are playing with is using Wapl-Wabbit. Wapl-Wabbit is another open source framework, really, really powerful. And its beauty is that it's designed to be run in a streaming fashion. So what we've done is we have one job which does the feature extraction. We have written it using mrjob again. And given our past impression data, we extract the features using mrjob. We store the feature files in S3. And then once again, for every grid point, we run Wapl-Wabbit on that grid point, right? And we are running Wapl. We've come up with a framework by which we can run Wapl-Wabbit on Mr. Job in one reducer. So we start a map reduce job with several reducers where each grid point is evaluated by each reducer. So each reducer is getting a copy of the data. And then at the end, we evaluate, each reducer is learning one model, right? And then we evaluate the performance of that grid point and on that training data. And then we figure out what is the best hyperparameter, and then we retrain our data on that hyperparameter, right? So now one of the most important aspects of this click-through rate prediction problem is in terms of how do you measure performance, right? So one thing you may have noticed is that we are training on only the winners of each auction, right? So for every auction that we did and we showed the winner, we take the past winners, and then we look at whether those ads led to a click or no click, right? And then we train a model, and then the model outputs click-through rates, right? And then we compute this mean cross entropy value, right? Now, you will notice that online, when we are actually applying our model, at that time, we are actually applying it to every candidate in the auction. So we learned something using only the winners of the auction, but now it is being applied to everybody, right? Now, therefore, you do a query, then all these potential candidates, they will be scored using that model that we learned earlier. And we will get a PCTR value, and then we also will get the bid price, as I had referred to earlier, using the auto bidding system. And let's say this guy wins the auction, right? And then he would be returned as a result. And then we would see whether this result led to a click or no click. And therefore, we could also once again compute what we call online MXC, which is once again I would take the probability of a click which was output by my model, right? And whether it got a click or not click. And I could once again compute the online mean cross entropy. However, we found in practice that online MXC, it does not correlate well as a measure of, as a true measure of performance in our online system. What we really need is an online metric which can capture the performance of all the auction participants, right? Because we are applying that model to everybody here. The trouble is that we can only observe the performance on the winner. We can only observe when we return the winner whether the winner led to a click or no click, right? Turns out that using calibration plots, calibration plots serve as a very good proxy to measuring our online performance. So the way to read these charts is for two models. So one is the status quo, which is the best model so far, and then there's the challenger model. So on the x-axis, I have the predicted click-through rate bins. For every group of impressions which are in that bin, I would compute this delta of observed click-through rate minus predicted click-through rate, right? And this line is basically the line 0, right? So when my observed click-through rate is less than predicted click-through rate, then I'm over-predicting, right? Because my predicted PCTR value was greater than OCTR. And if the values over here on the y-axis were greater than 0, then I'm under-predicting, right? Now, as you can see, the status quo model in our online system, when we were using online MXC, it came out to be it was supposed to be the best model in terms of online MXC. And we were like, hey, what's happening here? We thought our challenger model should be outperforming the status quo, but it seems that the online MXC is in terms of online MXC, the status quo is still the best. But turns out that if you look at the calibration plot, the challenger model is actually pretty well calibrated. It's actually more well calibrated than the status quo, because as you can see, the status quo has huge errors in this region. It is over predicting in that region. So some other challenges that I wanted to discuss briefly, in our click-through rate prediction system, so there's always this question of what is a feature and what is a model, right? So to us, when we get a query, at that time, the query is, let's say, on the mobile app, or it could be on the desktop, etc. So what is constant is the query, right? Now the advertisers could be from different categories, etc. So we want to use the same model for all the advertisers, right? So therefore, it makes sense to have one model for every page type, right? But because then we could actually this would perform better in terms of latency of the system, etc. But the advertiser category could be a feature, right? Then the other notion here is that of training frequency, as in how frequently should you be retraining. There is a high seasonality in our data, and as I alluded to earlier, some categories, they vary differently depending on the season. So, if we have trained a model for winter, it may not be the best model for the summer. So at what frequency should you be retraining? So some of these are challenges and questions we are still trying to solve. Some of them are still very open-ended. I just wanted to sort of highlight them and motivate to you what are the sort of interesting problems in this area. Then the other notion here is that of revenue versus relevance. So what I'm showing here is once the auction is complete, we have another lever, which is that of click-through rate threshold. So we say that if the winner of the auction is expected to have a very low click-through rate, then why should we even show that ad, right? Yeah, because at the end of the day, we want to show ads which are relevant, right? So as I said earlier, we want to delight our users. So if I were to move this threshold of minimum click-through rate all the way to 0, then I would be showing ads on every query, right? Which may or may not be relevant. I would maximize revenue, but maybe I have minimized relevance, right? On the other hand, if I were to increase this click-through rate threshold all the way to 1, then I would be showing very few ads. I would be only showing ads where I know with certainty that these ads are going to lead to clicks, right? So I've maximized relevance, but maybe I have hurt revenue. So where is the sweet spot? So this is basically a classic precision versus recall type of a situation, right? Some of the measures of relevance that we have are clicks, But we also have and are experimenting with other signals, which are in terms of signals further down the funnel. As in, after you click the ad, did the user look up the directions to the business? Did the user make a phone call, etc. Right? And we also have a crowdsourced list where people, when they see bad ad, they email it to us, and then we go and dig deep into why did we show this ad on this query, and we should do something about it. Is there a particular feature which we can add in order to actually make sure that we would not have shown ads across that category pair? So then one of the other interesting questions is that of cost versus accuracy. So the cost comes in terms of training cost. There is a cost to train every feature. Complicated features would require more training efforts. And there's also a cost at scoring time, right? So, some features, they may require, database lookups, etc. And at the end of the day, we want to be able to return an ad within tens of milliseconds. So we can't do complicated things, right? And also this cost, it increases with large number of features, right? So at runtime, when we are scoring a query, and we're scoring all the ads against that query, the more the features that you have, more Python objects you'd have to create. There would be more object creation time. There would be also more garbage collection overhead, right? So one way we deal with this cost versus accuracy trade-off is, I'll motivate it with this example. As I said, categories are an important feature for us. So one way of looking at categories is, for every category of advertiser, you make it a binary feature. Right? So you'd have thousands and thousands of features then, right? Another way is to basically just make that into one feature, where you say that, for Japanese restaurants, what is the average click-through rate I have seen in the past? For Korean restaurants, what is the average click-through rate I've seen in the past? And every time I see a Japanese advertiser, I will substitute that value as the feature value, right? So instead of using thousands of binary features, I would use one numerical feature, right? Of course, if I were to use thousands of binary features, it is more, the model that I would learn would be more accurate. But at the same time, at runtime, I would pay the cost of, more objects being created, etc. So on the other hand, if I were to use the CTR translation and convert it into one numerical feature, the model may be slightly less accurate, but the runtime cost would be lower. So then there's this other interesting notion of exploit versus explore. As I said earlier, there are some categories which are non-intuitive, right? Like showing karaoke ads when people are searching for sushi or Japanese. How can we learn such non-intuitive pairs, right? There's one way to learn all such pairs is by basically, just exploring all possible category pairs. But then we would show a lot of irrelevant ads as well. We don't want to do that, right? So there's another more systematic way of doing it, which is using exploit explore or multi-arm bandit type of techniques, where you basically, show ads of one category on searches of another category for a certain time in an explore phase. And then once you figure out that, hey, the click-through rates are okay, then you continue showing it. Otherwise, you don't, right? So those are some of the other questions we are looking into. And then the other aspect is that of model automation. How do you measure when your model, it starts to get worse because the traffic has changed, right? So to conclude, local advertising, it has a lot of very interesting challenges. It's very different sets of challenges compared to search advertising or social advertising or mobile app install advertising. And Yelp has a very unique selling proposition to local business advertisers, because Yelp users, they have a very strong intent to purchase. And Yelp can close the loop between a user and the advertiser, because we can not only optimize the eyeballs and the clicks, but we can also optimize signals which are further down the funnel. We can show that to the advertiser about, like, these were the people who made phone calls to your business. These were the people, who looked up directions, of course, in an anonymized fashion. And we can give them a report of, how many phone calls they got from our ads, etc. Right? So yeah, one of the last things I wanted to talk about was that Yelp, we like to engage with academia. And when I was in grad school, we had a dearth of good real data sets to work with. So one of the efforts that I'm involved with at Yelp is that of Yelp Dataset Challenge, which is a way to sort of outreach academia, we have released a data set for local businesses and reviews for local businesses in 10 different cities in the world, including actually Montreal. And we have 61,000 businesses in this set. We have all the business attributes, which are whether this business has parking, whether it's good for kids, whether it's romantic, etc. And we have all the reviews for all those businesses, and all the user data. So essentially, anything that you could get by crawling Yelp, we have made available only for these 10 cities. We don't want our grad students to keep crawling Yelp, right? So that's why we decided it's easier to just make it available to them. And people have been doing some fantastic research using this, from the whole gamut of using sentiment analysis to figure out, what are the sort of things people are talking about with respect to a business. And they have, one of the most interesting ones. In fact, we had a hackathon, which we call Yakathon in Montreal, which happened like a few months ago, where we basically asked the community of Yelpers in Montreal to just do anything they want to do with this data set. One of the winners actually, they took our review data set and they took our business attributes in terms of how expensive each restaurant is to predict home prices by neighborhoods in Montreal. So that was pretty interesting. And if you are in grad school and you want to play with some data, please go take a stab at it. We also run a contest internally where people, they submit visualization or a research paper that they have written using our data set, and they submit it to us. We run this contest twice in a year. The current ongoing contest will end, or the submissions will end on June 30th. And internally, our team of data mining engineers, we then evaluate those papers, and then we award cash prizes, as well as we enable students to go and present their research in conferences. So if you are in grad school, or if you know anybody who is looking to play with some interesting real data set, please go take a stab at it. So that brings me to the end of my talk. I'd be very happy to take questions, and you can reach me at my email address is over there, and that's my Twitter handle. Thank you.
Thanks so much, Soups. Anyone who has questions, please line up at the mic on
your right-hand side of the room.